Let's see if I can find. It may be that when I go to the book, that's where I left off at. Oh, yeah. Yeah, there you go. Oh, there you go. Oh, yeah, I remember that. I'm going to find one with a, well, let's see. That one looks reasonable. Oh, yeah, I should do that. But I think I better do, there we go. Let's do it on standard first. Okay, need to be that way. Okay, is there any other information? Oh, shoot, I need to get the problem statement too, because it tells you what HA and HB is. Okay, let's go to the bottom. So if we do this problem, we do one or two and then go about our way. So we've got A. Let's do this. We go from B over here to A. So PA plus gamma ZA plus rho VA squared over 2 is equal to PB plus gamma ZB plus rho VB over 2, because it's constant along the streamline. That's probably not the way the thing goes. It probably just goes straight that way. And first thing, we'll pick a datum that is right there. So if that's the case, then that's equal 0 and that's equal 0. And then you got a situation where this is one of those things where perpendicular flows. So if you zoom in on this and look at it, what you'll see is a pipe comes down, is sitting straight on top of this. And if somebody didn't mess up the construction here, the velocity is just flowing from left to right. It's not turning away or turning towards it. So what's funny is if you go perpendicular through here, you see only hydrostatic pressure, gamma H. So P at any point is hydrostatic. Now, if the pipe was messed up, and say it had to turn, there'll be a slightly higher pressure because it's slamming into here and shoving the water a little higher. But we're going to assume none of that's the case. And if that's the case, then the pressure at A, which I've done these, I would think A would come before B, but he's got B coming before A. So the pressure at A is nothing more than the gamma times the height HA plus rho VA squared over 2 is equal to, this one is the gamma HB plus rho velocity of B squared over 2. So this step was because of the manometers. So these things give you that step where you can replace that. Now if you go on from here, you got to figure out how to relate velocity A to velocity B. One way to look at these things, and this is the way I like to say you have location A, B, C, and D. I don't, but I have that. Pressure, velocity, and Z. So you got three things here. But you may have multiple points in the flow. And so this is one way to look at it. Do I know the pressure A and pressure B? I can actually find that. Do I know the elevations? Well, yeah, I know that. So here's an unknown and here's an unknown. For our case, there is no C and D. So how do we get this? Well, there's an actual extra equation. So you get Bernoulli's, it'll take you one equation, and continuity will take you the second. So you get two equations. You can relate these two through continuity. So this little chart sometimes is helpful if you've got multiple locations through there to figure out which of the two you should write about. And I'll find a problem like that later. So you got gamma. Okay, well, let me go ahead and do that. Velocity, area at A, velocity A is equal to area at B, velocity B. He told us these two things. That's weird. Okay. Told us those two things. So pi area A is 0.25 squared over 4. VA is equal to pi times 0.4 squared over 4. VB. So those cancel. So I don't know. I'm going to put the VA is equal to 0.4 divided by 0.25 squared VB. Let's see. So that is not. Well, where we go? Where we go? All the way to here. 2, 5, right? And then square that. I think I got it. 2 equal. Wait a minute, I forgot already. 2.56 dB. So this continuity, what you can do is take the VA and stick it right in there. If you do that, you'll have gamma HA plus rho times 2.56 dB squared over 2 gamma HB plus rho times VB squared over 2. Now, only thing you don't know is VB. So, well, I was in SI units. So this is nothing more than 1,000 times 9.81 times HA. What was HA? 0.25 plus 1,000, because that's the density, 2.56 VD squared over 2 is equal to 1,000 times 9.81. That's the gamma. Gamma is equal to rho times G. And then HB, which was 0.95, and that's that, and then plus 1,000 times the VB squared over 2. You can take out that, and that. You can say, I don't know. Here, I'll move this one over here, and I'll move that one over there. So what I'll get is 2.56 squared minus 1 from this one times VB squared over 2 is equal to 9.81 times 0.95 minus 0.25. Taking the 0.9 and 0.25 and getting rid of those. And then I'll get dB equal to square root of 9.81.95 minus 0.25 times 2 over 2.56 squared minus 1. Let's see if I wrote this well enough for this funny thing to calculate it for me. Let's see, did it actually? Looks like it did. So it looks like I get 1.57 dB, about 1.57. So let's see if we can find another. Okay, I was right here, wasn't I? Okay, there's that one. Wait, I saw another one that looked interesting. Let me see if I can find one with multiple taps on it. Multiple locations, that's what I'm looking for. Oh, wait a minute. Wait. It says, determine the height of H of the column. The velocity, is that associated with that? Yeah. If the pressure of the 16th water, velocity at C, okay, determine the height of the column of water and the velocity at C if the pressure of the water at the 6-inch pipe diameter at A is 10 psi. Water flow past this point, okay. Yeah, might as well do that. But that doesn't have multiple points that through the flow. Oh wait, this one might. A and B and C. Okay. This one might. Well, let me see if there's another one I can find that actually might have a better multiple point. That's kind of similar. Shoot, they're all. I don't see too much. Oh, wait a minute. Okay, so the water drains from the fountain cup to A to B. Okay. Determine the depth of water in depth. Determine the depth H of water in B in order the steady state to be maintained. Take D. What is D? Where is D? Oh, that D. Water drains from a fountain cup in depth to be H equal 50. Determine the velocity of the opening so that the steady flow is maintained. Well, yeah, I don't know. But there's a break in that problem. That's not a complete, but hey, but that may show the point that I'm trying to get across. We'll do that one, and then I'll have to copy the words separate because I'm not sure I have a whole lot of room to put both of those on there. So here, we'll put the picture there. Go back and get the words here. I'll go ahead and get both sets. There. Okay, a little over here. That way I can have them all together. I can move them around a little easier. Okay, so the water drains from the fountain cup at A to B. Okay, so that's the cup A goes to B. It's pretty obvious. That's to determine the depth of the water in B in order for steady flow to be maintained. Okay, so here's what we've got. I don't know. There's no tag for any of these things, so I'm going to tag them. And instead of he likes to tag them with letters. I'm going to tag them with numbers. So I'm going to say 1, and I'm going to say 2, and I'm going to say 3, And then I'm going to say like 4 right down here. So here's the thing. Bernoulli's has this, and the elevation in it. This time I have a location 1, location 2, location 3, and location 4. Hang on. I don't have to, but I am going to use because actually this is multiple problems broken apart. I'm going to use, so 4 itself and 2, I'm going to say is right at the base. So here, let me move this 4 up and say it's right there. And I'm going to say 2 is right here as well. So technically, we don't need this, but I'm going to go ahead. It doesn't matter how high you have this part, but I'm going to go ahead and say he specified that as, this is ridiculous, but here, 10,000 millimeters, just because. Just so we'll find out don't need it anyway. But it's basically setting up so I can find the datum anywhere. So if I pick 4, nothing. Okay, so he says the water drains from the fountain. The depth of the cup is H equal to 50. Okay, so I've got to go in here and pick that up. Point, okay, B, or 3. 0.05, is that right? 50 millimeters? Okay. And then 2, here. Here's what I'm going to do. I'm going to say roughly, I'll just say 1,000. Doesn't matter. So I'll just make that up so that the distance from here to here is 1,000. Just because I'm going to even use it as 1,000 meters. Doesn't really matter. And then that's to 2. And then here, 0.1. Now, this is dumb what I'm doing, but all I'm trying to do is put in here and show what and where how you could use this chart. So the pressure, do we know the pressure at 4? Do we know it at 3? Do we know it at 2? Do we know it at 1? Well, they're all touching atmospheric. So now we've got velocity at 1, velocity at 2, velocity at 3, and velocity at 4. What do we know about 1? Pretty much 0, and 3 is pretty much 0, because we've moved this spot enough off to the side so that it's 0, and we've moved this one off to the side enough so it's 0. So already we see one row with an unknown and a row right here with an unknown. But what we find out is the problem is split in 2. And this is the stupidity of what I just did. What I'll do is I'll change that to a big distance D plus 0.1 and a big distance D, where D can be anything. And so now we see right off what we need to do. If we write between here and here, we can end up with V2. If we write between here and here, we can end up with V4. But one of the things that has to be maintained is continuity. So now that I've done that and done the logic of going through it, let me do them individually. I just wanted to show that table because then you get an idea of what you need to do. It's not necessary. Yeah, let me get it out of the way now. So let's write between 1 and 2. P1 plus gamma Z1 plus rho V1 squared over 2 is equal to P2 plus gamma Z2 plus rho V2 squared over 2. The water sitting right here isn't doing anything. Okay, wait a minute. So he says take D to be 0.25. Where's D? Oh, D is at the bottom. Okay. Okay. So what we can find out about these two is they don't exist. We know that doesn't exist. The water's just sitting there. And we know, I'll put these things together so that gamma Z1 minus, move this over, Z2 is equal to rho V2 squared over 2. Then we move that around and we find out that V2 is equal to the square root of 2 gamma V1 minus Z2 over that. Okay, did I put that underneath? Right. And since rho G, I can just replace that with rho G equals square root of 2G V1 minus Z2. So I'll take a pause here for a minute and do an old dynamics problem. I drop a marble. Here's my datum. I drop it from rest. So the energy at this state is mgh. I want to know when it gets to this level, which is the z is equal to 0, I want to know the speed, 1/2 mv squared. So I set those equal. mgh is equal to 1/2 mv squared. The m's go away, the half goes over, and 2gh, the square root, that's equal to the velocity. If we look at real close here, what we find is, of course, this is labeled as V2. 2gh height difference is the same thing as that. So you can see the similarities between those old type of problems and these new fluids problems they're seeing. They're kind of the same. Okay, so you got that, and that's great. That's fantastic. I'll just move it to the side. And actually, I guess I can go ahead and do, hang on, give me a second. V2 is equal to 2. I'm in this thing where I can use 9.81. And then the height difference between these two, 0.1, you take the square root of that. I think it'll recognize all this. This says it's 4.42945. Now, let's repeat the problem between what essentially was 0.3 here and 0.4. And so P3 plus gamma Z3 plus rho V3 squared over 2 is equal to P4, because that's the 4 down here, plus gamma Z4 plus rho V4 squared over 2. And here, these are different. So different steps to the same problem. Pressure is the same. Velocity at 3 is just sitting there. It's like stagnant, floating around. So I get gamma Z3 minus Z4. Now, if I make this to be datum, then this just becomes H, which actually, does he tell me? Yeah, he tells me that this is 0.5. So this is equal to 0.5 meters equals to rho V4 squared over 2. Bring the 2 across and you get the same thing, V4, but with different, 2 gamma Z3 minus C4 over rho, which is the same thing as 2G times Z3 minus C4, the square root Okay, the Z3 minus the Z4 was 0.5. The G still ends up being 9.81. And 2, I'll do that. So V4 is equal to that. Now, what's funny is that kind of makes sense. This is a shorter distance than that. So, let's see. Oh, it did not recognize the 5. Okay, let's try this again. Let's see if it recognizes that. Oh, it did that time. 3.13209. Okay. So it's going a little slower than it's going up here. Okay. So he wants, I mean, I don't know. He's got all these different things. The water drains from fountain cup A. Determine the depth of the water in B in order for the steady flow to be maintained. Okay. The depth of the water, H. Where's H? Oh. Shoot, it looks like I'm not working on this problem. Looks like I'm working this problem. Because I went ahead and took that depth. Okay. The water drains from a fountain comes. It is H. And determine the velocity of the water at C and the diameter of the opening. See, I didn't read it close enough to realize these cannot be solved at the same time. They're two different problems. So since I've already taken that to be a half a meter, looks like I'm working this problem. Okay. Determine the velocity of water at C and the diameter of the opening D so that the steady flow is maintained. Well, now, okay. I already found the velocity of the water at C, the diameter of the opening. So what I've got to do, okay, so steady flow is being maintained. What that means, he's already told me that this is 20. And now he hasn't told me what this D is. The steady flow is being maintained. But these are actual velocities. That means A for V4 has got to equal to A to V2. But A2 is this, and it's 20 millimeters. So that's pi 0.02 squared over 4. V2 is equal to V4, which I have both V4 and the other. So pi, did he call it D? He called it a little d right there. Okay. A little d squared over 4. So continuity has to be maintained. These can be canceled. The V4 can be put in from here, and the V2 can be put in from here. And so what you get is D2, D squared, V4, 3.13209, and that's got to be equal to 0.02 squared times V2, which is 4.42945. So D has got to equal to the square root of 0.02 squared times 4.42945. I'm trying to write my handwriting really well. Oops, 209. So D, since that velocity is a little bit, here I'll calculate before I start talking. Okay, first of all, did it yet? Okay, so it says 0.02378842. So D is a little bit larger than this other. And the reason that has to be that way, the mass has to be maintained. since this height, okay, so I've already gone in and I'm doing the bottom problem. So now, since this height is higher than this height, this velocity is faster than this one. And so this one being the slower velocity means that the area has to compensate by being a little bit bigger so that the mass flow coming down this chute is the same thing coming down that. Oh, man. What about how's it killing me? Well, does that make sense? Should we call it a day or should we? Okay, so we'll call it a day. And then I'll try, you know what I'll try to do is I'll try to go through and I might do, because I mean, I'll be here at Friday because I do statics and dynamics. So I'll hang around for a minute if anybody's got questions. If nobody comes, I won't do a stream. But then if I don't, I'll pick the sets of videos that are associated with it. So this is a weird way of doing a class.